Now we are going to discuss winds, right?
ये तो फ्लैट पोर्शन इन पर थोड़ा सी क्लियर करेंगे।
कौन सा?
ये सब ट्रॉपिकल हाई नॉर्दर्न हेमिस्फीयर इज वीकर बट दिस कंटिन्यूअस।
Open the atlas. Open atlas. World map. Why subtropical high pressure area is weaker in the northern hemisphere as compared to southern hemisphere? Any map you look at here, you will understand it. Now look at the position of 30-degree latitude in the northern hemisphere and 30-degree latitude in the southern hemisphere, where ideally subtropical high pressure belt is expected to be formed, right? Any world map you open and you see that. Now in the northern hemisphere, the part of subtropical high pressure belt would be passing over the continents, right? Now during summer season, the continental areas will be heated and will have very high temperature on the ground.
Yes.
Subtropical high pressure area is basically an area produced by Coriolis force.
Yes.
So it is not thermally induced pressure belt. Dynamic. Now the moment surface temperature is very high, it will not allow the subtropical high pressure to develop over the continental areas. So the continuity of the subtropical high pressure belt, ideally we have discussed that it should be around 25 to 35 degree latitude, will be broken over the continents during summer season. Hope you understand the contradiction between, because fundamental reason for the formation of temperature is formation of pressure belts is temperature, right? So if on the ground the temperature is very high, it will not allow the subtropical high pressure belt to develop. So that's why the subtropical high pressure belts are more popularly found in the oceans in the form of cells, right? That's what we have read, Azores High and Hawaiian High. Similarly, if you look at the latitudinal position of 60-degree north latitude, over the continental areas during the winter season, the temperature will be so low that it will not allow the low pressure to develop properly. So that's the reason why northern hemisphere dynamically induced pressure belt is less stronger, but thermally induced pressure belt will be more stronger because of the impact of land masses over the temperature. Hope we are clear. Winds. I hope we have learned that motion of air is associated with pressure gradient force, and that is a force which is produced because of the difference in the value of pressure system in the adjacent area, right? Let's first talk about the motion in air is actually because of pressure gradient for the fundamental factors, but there are several factors which affect the motion and direction of wind, including the velocity and the direction. But definitely when you look at the factors affecting wind motion, that will be the heading. Factors affecting wind velocity and direction. The greatest factor will always be pressure gradient force. Right? The fundamental reason behind the movement of air. Pressure gradient force, I hope there is no doubt about pressure gradient force, hope we understand it. Now, if you look at the pressure gradient force, the direction of pressure gradient force is always perpendicular to the isobars. Wherever you don't understand, let me know. Perpendicular to the isobars. Right? It affects the velocity of the wind, which is directly proportional to the pressure gradient force, right? Now, as per pressure gradient force, the direction of the wind is determined. It determines the direction of the wind again. Fundamental factor in determining the direction of the wind. Sometimes it may be confusing when you are given a statement in the preliminary examination that the most fundamental factor affecting direction of wind, generally you will confuse with Coriolis force. Coriolis force is a secondary factor, it's not a primary factor, right? Direction of the wind is primarily determined by pressure gradient force. Though Coriolis force is an acting agent, they may not allow the wind to have its direction exactly as per determined by pressure gradient force. That's a different issue, right? So as per the direction of the pressure gradient force, what should be the direction of the wind then? If pressure gradient force is single-handedly determining the direction of the wind, what will be the direction of the wind? Perpendicular to the isobars, right? So if suppose there are few isobars, this is the direction of the pressure gradient force, and this will be the direction of the wind also as per the pressure gradient force. However, the wind does not really flow in the perpendicular direction or perpendicular to the isobars, right? It has curved direction. It makes at an angle much lower than 90 degree. That will be determined by the intensity of Coriolis force. If the Coriolis force is smaller, then it may have different direction. If the Coriolis force magnitude is much higher, it may be making lower angle with the isobars, right? So second factor which is affecting wind is Coriolis force, right? Now the Coriolis force is generally acts perpendicular to the pressure gradient force, but always acts perpendicular to the wind direction. Like NCERT writes, perpendicular to the pressure gradient force, but that is not always true, right? Initially, it may act perpendicular to the isobars pressure gradient force when it started moving from the high pressure area towards the low pressure area, right? Initially only it is true that the direction of the Coriolis force is perpendicular, but later on it keeps on increasing and changing its direction. So basically, if you read, the direction of Coriolis force is perpendicular to the isobars. We have already discussed about Coriolis force, right? It causes deflection of wind rightward in the northern hemisphere, leftward in the southern hemisphere. It is produced because of the rotation of the earth, right? Now, its magnitude is determined again by the velocity of the wind. Higher the velocity, greater the Coriolis force. So, magnitude of Coriolis force is determined by two factors basically. One is the velocity of the wind. Second is the latitude. 0 at equator and maximum at poles. That's what we have written earlier, that it is directly proportional to the latitude. Right, we don't need to go into why and what, into the physics of Coriolis force, because they'll never ask you that. Simply remember that with the increasing latitude, the Coriolis force magnitude will increase. Now, here onward, this is the basic concept that will be anywhere. Now, the question which will be framed in preliminary examination would be more than that, and the answers when you are writing in mains examination will require this information. For example, if the statement is asked in preliminary examination that the wind will be having much straighter and perpendicular direction with respect to isobars along the equator, true or false? Wind along the equatorial region, close to the equatorial region, will be perpendicular to the isobars, true or false? True, because of zero Coriolis force, and wind will be making minimum angle around the poles. True, right? So these kind of statements are inferred statements, where the fundamental concepts will be used to make statements. To remember this thing, an interrelationship of various concepts.
Sir, एक question. ये कोरियोलिसिस फोर्स आइसोबार के परपेंडिकुलर लग रहा है?
नहीं, किसने बताया? प्रेशर ग्रेडियंट फोर्स आइसोबार के परपेंडिकुलर लग रहा है.
The direction of Coriolis force will be perpendicular to isobar.
No. लिखवा दिया है? अच्छा. The direction of pressure gradient force will be perpendicular to isobars. हाँ.
तो भी लिखा है.
अच्छा.
कोरिलेस फोर्स डायरेक्शन क्या
नहीं, कोरिलेस फोर्स का डायरेक्शन परपेंडिकुलर टू विंड होगा, नॉट प्रेशर ग्रेडिएंट फोर्स, perpendicular to wind. Okay, correct it. Slip of tongue, right? So when we talk about coreless force, now if you look at here, it's a relationship with pressure gradient force. Now velocity of wind is directly proportional to pressure gradient force. Coriolis force is directly proportional to velocity of wind, right? So can we say that Coriolis force is directly proportional to pressure gradient force in terms of its magnitude? ज़्यादा हो रहा है?
वो तो होना ही चाहिए
सर, बट इट इज प्रोड्यूस्ड ड्यू टू रोटेशन ऑफ अर्थ. रोटेशन ऑफ अर्थ का इससे क्या बढ़ती है?
Rotation of the?
It is produced due to rotation of earth.
Uh-huh.
It should be
No,
constant.
it is produced because of that, but there are various other factors which affects Coriolis force magnitude. That's what we have read earlier. Just now, there are the two factors which affect the magnitude of Coriolis force. One is the velocity of the wind, another one is the latitude, right? So when we talk about velocity of wind, so if Coriolis force is directly proportional to velocity of wind, which is directly proportional to pressure gradient force, so definitely in that particular relationship, Coriolis force is directly proportional to pressure gradient force, right? Now, if you look at the ultimate direction, that means when the Coriolis force can ever attain a direction which is exactly opposite to pressure gradient force. Is it possible? Or we can say that ultimate direction of Coriolis force is exactly opposite to pressure gradient force. Now let's see what actually happens. Suppose this is a high pressure area and this is a low pressure area. So what is the direction of the pressure gradient force? Is this high pressure to low pressure, right? Always. So if pressure gradient force is taken as a single entity, as a only entity, then we can make a statement that pressure gradient force will always want the wind to move away from its origin point, right? Always want to move wind away from its origin point. Now let's take Coriolis force as an individual and separate independent force. So what if Coriolis force is allowed? Turn right if it is in the case of northern hemisphere. Turn right, turn right, turn right, turn right, turn right. So what is the ultimate aim of Coriolis force? To bring the wind back to its origin point, right? Now let's see. Suppose a force is applied on my body, right? One force wants me to move always away from here. Another force is bringing me back. So can't we say that the direction of these two forces are exactly opposite to each other? One force wants me to move in this direction, and the one force ultimately wants me to bring it back here. So the direction of the wind is, direction of these two forces are exactly opposite to each other. Though there is a different factor that this force is much bigger, so I may be dragged as per this force, but this force is slightly smaller. That's why I will be turning. Whether it is rightward or leftward, that will be determined by the difference in the hemisphere. Hope you understand? So these two forces ultimately are opposite in direction, right? Now, if both these forces are balanced, are equal in magnitude, what will be the direction of the wind? So, for example, like my body, if both the forces are equal, both the forces are equal, and if my body is supposed to move, let's say, in the case of wind, it will be moving.
So circular.
Circular.
Yes.
So if suppose, let's take that example of whether it will be circular or not. Let's say suppose this is a high pressure isobar and it keeps on decreasing, keeps on decreasing, keeps on decreasing. This is a low pressure isobar, right? So as per the pressure gradient force, this is the direction. As per the Coriolis force, this is the direction of the Coriolis force, right? What will be the direction of the wind? Circular means, suppose it's coming like this, right? So here it has defied pressure gradient force, because wind is moving from low pressure to high pressure area in this area, which can never be possible. Getting that point? Because pressure gradient force is the fundamental force, and it cannot be defied by a secondary force like Coriolis force. So Coriolis force at the most can be equal when it attains its maximum. That means all the factors which supports Coriolis force is at its best. Even in that situation, Coriolis force can at the best be equal to pressure gradient force. It can never be more than that. It cannot defy the basic principle, fundamental principle of air motion, which is guided by pressure gradient force. Getting that point? So the circular motion here is not possible right now. But there are some circumstances where it is possible. I'm just taking two forces. If both are equal, then the direction of the wind, direction of my body will be like this, like a pendulum. So can we say that the direction of ultimate wind, when these two forces are equal, will be perpendicular to the direction of these forces or parallel to the isobars? When it has started moving from here, after a point of time, it will start moving like this. So I'm talking about this situation where it is possible that when the Coriolis force and pressure gradient force is equal, the wind will start moving parallel to the isobars. The wind which moves parallel to the isobars are called geostrophic wind. Right? The wind which blows parallel to the isobars are called geostrophic wind. Hopefully we understand geostrophic wind. Jet stream is the best example of geostrophic wind. The third factor is called frictional force. Okay. Frictional force is the force generated because of the undulation on the Earth's surface. Let's say presence of mountain, different height of a mountain. When wind is moving, let's say from plain area towards plateau area, so the velocity of wind will be decreased. When the wind is moving from plateau to mountains, windward side of a mountain velocity will be decreased, leeward side of mountain velocity will be increased, right? So generally when we talk about the frictional forces, that affects the wind velocity in a negative manner, right? So frictional force reduces the wind velocity. Right? Now, frictional force is because of undulation. So can we say that ocean surface will have least frictional force? Right? Continental areas will have high frictional force. Surface of the earth will have higher frictional force as compared to the atmospheric layer. When we move after a certain meter, the frictional force will be zero. Right? Especially horizontal direction, frictional force will be zero. So, whenever frictional force reduces the velocity of the wind, That means it reduces the magnitude of the Coriolis force as well. Basically because Coriolis force is directly proportional to velocity of the wind, right? So when we talk about any factor which reduces the wind velocity means reduces the Coriolis force. So we can say that Coriolis force is inversely proportional to frictional force. So the third factor which will affect Coriolis force is frictional force. We didn't talk about earlier basically because we didn't have the understanding of frictional force. Now frictional force is maximum close to the ground. So as a result it will not allow the Coriolis force to attain its maxima. Any doubt? Because one factor which is reducing Coriolis force.
Sir, close to the ground.
Right? So it will not allow the Coriolis force to attain its maxima. The moment it has not allowed to attain its maxima, it cannot match up with the pressure gradient force. Right? I mean, we can say that the Coriolis force can never attain its maxima on the ground because there is one factor available on the ground which will keep on reducing its magnitude. That means Coriolis force can never balance pressure gradient force. That means geostrophic wind cannot be produced on the ground. Is it clear or not? Just try to correlate. It cannot be created. So that means geostrophic wind is basically an upper air phenomenon. Clear?
Sir, if you say कि factor Coriolis force 0 है, then क्या friction force पे impact होगा? Maximum friction force.
No. Other way around is not possible. इसको mathematically नहीं देखना है.
नहीं.
If Coriolis
Rate करें. अगर कहीं पर force बहुत कम है, तो friction force ज़्यादा होगा?
नहीं. इसलिए ज़्यादा नहीं क्योंकि one is affecting the other. It's not a two-way system. Because the reason for the origin of frictional force is surface undulation, right? So if surface undulation, like in the equatorial region, if the undulation is there, friction force will be equal. If suppose in the equatorial region and the temperate region, the surface undulation is similar, so friction force will be similar, right? One place Coriolis force is 0, another place Coriolis force is maximum. So the effect of magnitude of Coriolis force is not only determined by frictional force. There are various factors which determine. Frictional force is produced only because of undulation on the surface of the earth. So frictional force will affect Coriolis force, but Coriolis force will not affect it. The reverse is not true. So we have written that in directly proportional, but the reverse is not true. Remember it.
Sir, big lakes वगैरह में जो
Big lakes में नहीं. Even water, when we say that it is having lesser frictional force, but the moment wind is flowing over the water surface, it will generate waves, and that waves will act as a barrier for that. Like for example, in the urban areas, right now we are sitting here, we can't feel the actual speed of wind because there's lots of buildings surrounding it. And the moment you go on to the 8th floor or 10th floor, the velocity will be much higher. So, on the closer to the ground, like if you move into the Faridabad area, move into Gurgaon area, outskirts of Gurgaon, in the field, you will feel that wind velocity is much higher. The same is not felt inside Delhi. It's basically because the building acts as a undulation, creates a lot of frictional force, so you don't have proper wind flowing into this area. Right? if you, like for example, making bigger towers, let's say like Dubai ka Burj Khalifa or any such towers, will always be leaning towers, because the moment you move higher, the shear wind velocity increases. The wind velocity increases very high. So if wind velocity is very high, it may not be able to bear the brunt. So they'll always move slightly like this. They'll be much more flexible. So they'll lean down, then they'll come back, then lean down, they'll come back. And that's why construction of buildings at a much longer story, higher story buildings are very, very tough, where the mathematician and the physics is applied, and the wind velocity and its impact on the building and all things are taken into account. That's why always it will be narrow. Going up, it will be narrower and narrower. Now, what happens in the case of a circular isobars? Like for example, cyclones. When the low pressure is very intense, especially in a local area, in a smaller region. Let's say suppose these are circular isobars. A low pressure is developed in the center. And when isobars, spacing between the isobars is very narrow, that means very steep pressure gradient force. That means quickly, isobar is changing very quickly. That's why you need to have several isobars denoting a very smaller area. So what will happen? The pressure gradient force is very steep. So wind velocity will always be very high. So the Coriolis force will also be very high. Now let's say suppose this is the center of this area. So anywhere the direction of pressure gradient force will always be like this. Wherever the wind is flowing, the direction of the pressure gradient force will be towards the center of this, right? Hope you understand? Now let's say the Coriolis force, which increases its intensity and magnitude towards the center. So what will happen? It will start moving. So after a point of time, it is going to cross the isobars. Very much a possibility. But again, that will defy the basic principle. So what will happen? Close to the ground, frictional force will reduce the Coriolis force, right? And ultimately what will happen? A balance will be achieved between frictional force, pressure gradient force and Coriolis force, which will force the wind not to get out of the isobaric surface, rather it will start moving parallel to the isobars. Like this way movement, leaving the center. When you read cyclone, the center of the eye or the eye of the cyclone doesn't have any wind, just like a well. And you all must have seen the whirlpool, at the dust devil जिसको बोलते हैं. एक छोटी सी चक्री घूमेगी, कभी देखा होगा नॉर्दर्न प्लेन में गर्मी के दिनों में. It will have a circular movement without having anything in the center. The dust will be moving like this, round. There will be hollow in between the central part. That circular isobars produces the circular wind. That is called gradient wind. So we can say that gradient wind is a sister of geostrophic wind, in the sense that they run both, in both the cases the wind blows parallel to the isobars. However, in geostrophic wind it is a linear isobars. In the case of gradient wind, it is a circular isobars.
So then what's the upward force?
That low pressure, whenever a low pressure is developed, so the central portion will be heated up and the air will start rising, right? So geostrophic wind is produced because of Coriolis force. Gradient wind is produced because of temperature, very intense heating of the ground. Gradient wind is basically a local phenomena. Geostrophic wind is a regional phenomenon. It's a much larger, coverage area will be much larger and bigger. Hope we are clear. The isobaric surface will be linear in the case of geostrophic wind. This is an upper air phenomena, this is a ground phenomena. Types of winds. winds will always be associated with pressure belts. That means wherever there is a variation in pressure system, there will be movement of air, and that will be if it is moving in a horizontal direction, there will be wind. Right. Now, the variation in pressure is global level variation. That means we can see that global pressure system, there will be regional pressure system, and there will be local pressure system or local variation in the pressure system. Hope you understand that, right? When we say global pressure system, that means we have 7 pressure belts what we have talked about, right? That system produces definitely wind of type that's what we call primary wind. That's first type of the wind. Primary wind means those winds which are associated with the primary pressure belts. That is 7 pressure belts what we have talked about. The same wind is also called planetary winds, because they together cover, at least on paper, the entire planet. They cover the entire planet. That's why they're called planetary wind. They're also called permanent wind. Only because of one thing, that their direction is permanent throughout the year. Because the direction of the pressure gradient force in the primary pressure belts will always be permanent, right? So the direction of the wind will always be permanent. That's why they are called permanent wind. And when we say permanent wind, the only thing which is permanent is its direction. Its origin point, its destination, all will be different in different seasons. For example, the wind which is coming from subtropical high pressure area towards equatorial low pressure area will always have similar direction throughout the year. But since subtropical high pressure belt shift northward in the northern hemisphere summer, its point of origin or zone of origin will be different. When it is actually in the equinoxes, it will be different. When it is in the southern hemisphere, it will be equatorward, in the northern hemisphere moving. So that's why the origin point will change, and the location of ITCZ, intertropical convergence zone, will determine the destination of wind. If it is located northward, the final destination of the wind will be northward. If it is located southward of the equator, that will be there. If it is at equator, it will be at the equator. Convergence will be at the equator. So the only thing which is permanent is its direction, nothing else. And that's what make regional pattern different, that here the direction is not permanent. They are called secondary wind because they are developed because of the secondary pressure system, not the primary pressure system. Right? They are also called periodic wind. That's the fundamental difference between the primary and secondary wind. Periodic wind means they change their direction periodically. What do you mean by periodically here? That means temporally. That means with time. So they change their direction with time. That's why we call it secondary wind or periodic wind. The best example of such periodic wind is monsoon. So the moment you write monsoon, you can start with monsoon is a periodic wind. Monsoon is a secondary circulation. monsoon is a regional scale circulation, right? Local is also called tertiary circulation or tertiary wind because they are the pressure system of tertiary level. They are produced because of variation in pressure system at local level or smaller area, and that's why they are also called local wind. They may have and may not have a fixed direction, but they are temporally and spatially very confined. They may not be blowing throughout the year. Right? They might be for a season, maybe intra-seasonal pattern. For example, Lu is the most popular local wind of the northern plain in our country. Right? If you look at the Lu, that is even the entire summer season do not experience Lu blowing. It is the intense heating during a particular period of summer, you will have dominance of Lu, which causes sunstroke in the northern plain area. Right? Similarly, the very good example is Chinook. Chinook is a warm wind flowing in the Rockies, especially during winter season.
Where?
Sorry?
Where it goes?
Rockies, Northern America. Right? So obviously that warm wind during winter season, that too in temperate region means mazedar ho jayegi. Like for example, if the questions are asked, discuss the impact of the local wind. So you can take several examples, especially warm wind in the colder areas, cold wind in the warmer areas will definitely have a different impact on it, right? So that ways we can look into it. So there are basically three types of wind as far as their origin, their movement, direction is concerned. Let's talk about the permanent winds. There are three types of permanent winds. One is called trade winds. They are also called tropical easterlies. Basically because they are flowing from easterly direction, roughly. And they flow in between the tropics. Roughly. Technically from subtropical high pressure area towards equatorial low pressure area. Now theoretically what we have read, let's say suppose this is 0 degree equator. So what we have read that equatorial region produces equatorial low pressure belt. Let's say subtropical high pressure area of both the hemisphere, southern and northern. Now what will be the direction of the trade wind in the northern hemisphere and southern hemisphere? You can easily understand by applying the principle of Coriolis force, right? So when it is coming, the direction of isobars will be like this, but the direction of wind will be slightly rightward. So the actual direction of wind will be something like this. Right? Actual direction of southern hemisphere trade wind will be something like this. Now the deflection is shown is almost in a straight direction. Why? Because it is moving in an area which is experiencing decreasing Coriolis force. So the tropical easterlies wind or trade wind is somewhat following the direction of the pressure gradient force. They are very close to the direction of the pressure gradient force, close to the perpendicular of isobars. Right? Now if you look at the direction of the wind, if it's treated as north, let's say north, south, east, west. So it is moving from northeast towards southwest. It is moving from southeast towards northwest. Northwest. That is roughly from east to west. So that's why they are called tropical easterlies. So direction, that's why simply you can call northeast trade means northern hemisphere trade wind. Southeast trade means southern hemisphere trade wind. Winds are always named from their origin point of view. Right? When we say windward side, this side of the mountain, leeward side, opposite side of the mountain. Now look at here, there are several information which we can easily conceptualize, not to forget forever, I hope. This region is nothing but a region of convergence, right? So we can say that it is a convergence zone. We have already learned that all the low pressure areas are areas of convergence. Convergence of what? The winds coming from two tropical areas. So whenever there is a meeting of two nations, we call it international meet. So there is a wind coming from two tropical areas and meeting, we can say that intertropical meet, right? So that's why this zone, the same equatorial low pressure belt, what we have theoretically discussed, that would be developed in and around 0 degree equator, is also called, that zone is called intertropical convergence zone. Intertropical Convergence Zone, ITCZ. Now this is a more appropriate term. Intertropical, to denote that low pressure, ITCZ is a more appropriate term as compared to equatorial low pressure belt. Why?
Because it is the cause of the low pressure.
No, both are the same. The only thing is that when we say equatorial low pressure belt, we take an impression that it is geographically fixed.
Yes.
Because equator is geographically fixed line, it is a fixed latitude. But equatorial low pressure belt in true sense is a dynamic term which keeps on oscillating northward in the northern hemisphere and southward in the southern hemisphere. So that's why when we say intertropical convergence zone, that is a more appropriate word, because that convergence may be north of the equator, may be at the equator, may be south of the equator. So that's why intertropical convergence zone is an appropriate term. Now the geographical equator region, when we talk about, or the convergence zone, the central portion of the convergence zone is free from wind, largely free from wind. Why it is so? Like for example, there is a two convergence zone coming, two winds are coming, and then imagine, just like ऐसा तो होगा नहीं कि आए ये हाथ मिलाइए अस्सलाम वालेकुम वालेकुम, let's move up. चलिए बात आगे बढ़ाते हैं. ऐसा तो होगा नहीं. They'll come, join together, then rise sharply. And second thing is that the low pressure area is not a line, it's a zone. So let's say this whole class width is the equatorial low pressure area. So now the moment which is wind is converging, so they will start rising in the margin of the low pressure itself. Right? When they are coming, they will not come and hit each other. Rather, they will come and start rising in the one portion. That's what will make difference. Will differentiate between subpolar low pressure belt and equatorial low pressure belt. You can easily differentiate. Generally, in NCERT, it will be directly written, and most often we learn also that way, that equatorial region is a doldrum, is a calm zone. So if it is a calm zone, why it is not subpolar low pressure? Why subpolar low pressure belt is not a calm zone? Both are convergence. So the moment you understand the basic concept behind it, you can easily differentiate between the similar features. So low pressure is coming in that convergence zone, the air will start rising. Now look at here, the air will actually meet far above the ground. Right? So this ground will be windless zone, wind free zone, and that's what calm zone, and that's what in Greek term it is called doldrum. So the equatorial low pressure belt is basically an area also called doldrum, that is calm zone. It is the earlier explanation. That older days we used to believe that equatorial region is a calm zone, is a windless zone. But in actuality it doesn't happen. There are some winds. Presently has been discovered after a lot of studies and research that winds blow in the equatorial region. They are generally blowing from west to east in the doldrum belt. And that's why they are called equatorial westerlies. Best developed in Atlantic Ocean. This equatorial westerlies is very much well found in Atlantic Ocean because of its perfect shape and distance within the continents. But it is also found in every oceans. Least developed in Indian Ocean because of the monsoon system. Now equatorial westerlies, why it is produced? Because of the convergence of two trade winds. Or you can say that ground effect of convergence is the equatorial westerlies. Let's, for example, okay, write down. After that, I'll tell you.
So, irrespective of the presence of continents,
Hmm.
it will converge and form every time equatorial westerlies.
Yes. But if it is continental areas, that will be perfectly suitable for its convergence and the formation of equatorial westerlies. Let's say, suppose, imagine that this particular line is equator, right? Now the wind is coming from this direction and this direction. They are colliding. Just imagine we are throwing water from the same line, same direction over this wall. Because that can easily be visualized. So when we are throwing water on this wall, one from this side, another from this side. So when the water is colliding, portion will rise. But if there is any movement in the middle, that will move like this. Can you understand that? Right? So when a larger chunk of wind, now imagine trade wind in three-dimensional figure. They are not actually confined in few meters of the ground. They might be covering 4 or 5 kilometers. So when they are converging along the equatorial region, and a greater portion of that will rise, but some portion might be covering the middle areas. So this way it will go, and convergence will produce wind in the middle of that convergence zone. That's what we call equatorial westerlies, because it blows from west to east direction. Is that
So
clear?
why direction is west to east? It can be east to west.
Yes, it can be east to west. अब पानी अगर इधर से फेंकेंगे उधर से फेंकेंगे, दीवार है वहां पे तो क्या होगी? कभी हो सकता है ईस्ट टू वेस्ट. Like you are talking about, this wind is going like this. This is like this. But let's say convergence. Look at the convergence and something is blocking it, let's say, suppose. If you see Atlantic Ocean, help you understand that. Atlantic Ocean, here you have South American portion, right? Here you have America, then you have Africa right here. Now the wind which is converging here, what will be the direction of the resultant wind? That will always be like this.
Yes.
Right? So because convergence is along the margin here. Here there is no convergence, they are moving like this. So they are free, their speed will be increased. When they are moving down slope, their speed will be increased. So they can overcome that. The moment they are upslope, moving from ocean towards the continent, their speed will be decreased. So they will be piling up here. A wind, simple principle of pile up, you can understand, and why the air should rise. That's a much deeper principle basically for optional student. But just you can imagine it. Okay, when the wind is rising over a greater height. So let's say suppose it has started rising here. Initially they are coming from ocean surface. Now they are supposed to rise along the margin of the continent. So the speed here will be more. Speed here will be less.
Yes.
Right? So relative speed is different. So pile up of air will deposit here. So they will start rising. That's why it's not necessary that all the wind will rise over the slope of the Western Ghat. Good portion of wind will rise much before the Western Ghat in the vertical direction. Right? So that rise is associated with the convergence, and the consequence pile up of air will increase the air content. Right? So whenever the convergence is in this direction, the high pressure will be developed with respect to the middle part. So that the wind will move from west to east and is called equatorial westerlies. Right? So when we learn trade wind, they are nothing but the wind which is coming from subtropical high pressure towards equatorial wind low pressure. Equatorial low pressure belt is also called intertropical convergence zone. Intertropical convergence zone is a dynamic term which keeps on changing its location northward, equatorward and southward depending upon the seasonal variation in temperature, or we can say thermal equator. You remember thermal equator? The highest value isotherm. So highest value isotherm will determine the location of intertropical convergence zone, and the highest velocity, highest value isotherm, that is thermal equator, its location will be determined by the vertical position of sun's rays. Right? If the vertical sun's rays is located in the northern hemisphere, the thermal equator will be in the northern hemisphere, the ITCZ will be in the northern hemisphere. Right? If vertical sun's rays is at equator like equinoxes, so the convergence will be there, ITCZ will be there. In the southern hemisphere summer, it will move southward. That's how the shifting of pressure belts and the location of ITCZ and wind will take place. Hope we are clear. It's called trade wind basically because of a nonsensical reason. Of the medieval period, it was very important because for the traders and sailors, it's used to help because the permanency of the direction will always help them sail through the oceans.
In that zone, in the North American zone, it's not pile up.
Everywhere. It's not North American side. The moment any friction force is there, air will pile.
What about the consequence of piling of the water
At the water. That's what the downwelling. And when we learn the ocean currents. So that's how when the ocean currents in the offshore zones you will have cold currents. The onshore zone you will have warm ocean current. Offshore zone is frictional drag. Onshore zone is pile up. So the sea level along the onshore zone will be 1 to 2 meters higher than the offshore zone. And that pile up of water will result into ocean current and downwelling. That's a different issue we'll discuss in oceanography. There are something which we should always apply common sense. Like you could ask a question that ports. So port is definitely important with respect to depth of water. Right? So depth of water may not necessarily be determined by 1-2 meter of sea level rise, and it has to be, like for example, most of our natural harbors is in the western coast. Western coast are more known for its ports as compared to eastern states. So there is a reason of slumping and all. So pile up of water may have be a very secondary or third factor or maybe 10th factor as far as the port location is concerned. Right? उसको अप्लाई किया करो, कभी भी सोचो ना तो उस चीज को. व्हेन वी टॉक अबाउट पोर्ट्स, तो डेप्थ ऑफ वाटर, डेप्थ ऑफ द वाटर एक माइनर फैक्टर होगा कि अगर 5 मीटर का या 2 मीटर का उठ जाए पानी किसी वजह से तो वो माइनर फैक्टर होगा. हाँ, उसको जैसे टाइडल पोर्ट्स, तो कुछ टाइडल पोर्ट्स हैं डेफिनेटली इम्पोर्टेंट, बट फर्स्ट प्राइमरी रीजन विल बी इट शेप द लोकेशन ऑफ द कोस्ट, द शेप ऑफ द कोस्ट, वेदर इट इज सेव्ड फ्रॉम द waves or not. That's what you call harbor. Harbor और port में fundamental difference size का. मैं फिर चला जाऊंगा दूसरी तरफ, छोड़ो उसको. I will come to the secondary wind. Trade wind के बाद second wind is westerlies. Westerlies means the wind which blows from west to east, right? The wind flows from subtropical high pressure towards subpolar low pressure. I hope we remember it. The descending air, the subsidence of air over subtropical high pressure belt, then wind moving into poleward direction and equatorward direction. So equatorward direction will make trade wind and poleward movement will make westerlies, right? Subtropical high pressure belt is also called horse latitude. Horse latitude is basically because the high pressure in the subtropical high pressure area when the air is descending. So now imagine this is the belt of high pressure area and the ship is coming from that area. So they'll have normal pressure the moment they enter into this latitude. So the descending air current will create more pressure. So the ship, which might not be sinking in that area, it might start sinking in this area if it is overloaded, right? So extra pressure of the descending air current pushes the ship downward and they may start sinking. In that case, what you are supposed to throw to lose weight, in the medieval period especially, you can't throw humans and you can't throw goods because they are more important than humans. So the only thing is left is horses or animals, which is generally used for transportation and they are carried on the ships. So they used to throw their horses in the middle of that latitudinal position. That's why it is also called horse latitude.
So means the extra weight which descending winds
Air will put on the ship. They will start sinking. Now in both the hemisphere, the wind will be moving from subtropical high pressure belt towards subpolar low pressure belt. In the northern hemisphere, look at here, the direction will be like this, turning rightward. In the southern hemisphere, the direction will be turning leftward. So in both the cases, it is westerlies, west to east. Hope we understand this, right? Now the deflection will be far, far more as compared to trade wind. So trade wind roughly moves in a straight direction, but westerlies will bend and turn intensely rightward. So after a point of time, they'll appear as if they are blowing from west to east, but they can't be perfectly west to east because then they will become geostrophic wind. If they are perfectly west to east like this, parallel to isobar geostrophic wind, which is not possible in the ground, right? So they are called westerlies, which are moving from subtropical high pressure belt towards subpolar low pressure belt, right? Now here, the westerlies of northern hemisphere, you can write down also, westerlies of northern hemisphere is much weaker as compared to its southern counterpart. Westerlies of northern hemisphere is much weaker as compared to its southern counterpart because of the discontinuity and weaker subtropical high pressure belt. The homogeneity of southern hemisphere water surface, produces more moisture in the wind. Making the wind heavier and the permanent and stronger subtropical high pressure belt, increases the velocity and strength of westerlies. Increases the velocity and strength of the westerlies in the southern hemisphere. In the southern hemisphere. Making it much stronger. So they are nicknamed as roaring 40s, roaring 40s, furious 50s, and shrieking 60s, at 40, 50 and 60 degree latitudes respectively. At 40, 50 and 60 degree latitudes respectively.